Hello everyone, my name is Van der Tung. Today we will present Chapter 8. There are 3 presenters including me, Đức Nghĩa Vũ and Ihan Song. Because the content of our presentation is quite short, I will represent the other presenters to present the whole chapter. Our presentation refers to the textbook on knowledge graph published in Morgan and Clayton Publishers 2021. This is the contents of our presentation. There are 3 main sections: completion, correction, and other refinement tasks. Thus, within each section, there are some small subsections that we will discuss in details. Let's move to the first section, completion. In this section, we will step by step discuss the incompleteness, geo link prediction, tile link prediction, and identity link predictions. We know that knowledge graphs are characterized by incompleteness is features of knowledge graph. So the term of knowledge graph completion aims at filling the missing edges. The task link prediction is to predict edges, though deemed to be correct, but not given intent by the knowledge graph. The targets can be geo links with arbitrary link labels, or tile links with label choice, or identity links with label CMS. Let's take an example. As you can see in the figure 5.2, the data graph representing the transport routes in Chile. There's the connection, bus connection and flight connection. There are some direction with both sides, and the other lanes are only one side. For example, if we consider these links, this link of the fly links, there the links has both directions. But if we consider the bus link, there are some bus link having both direction. But there are some bus links having only one direction. The bus link from San Pedro to Moon Valley to Piedras Rojas to Los Flamencos, they have only one direction. So if given thus most bus routes observe return services, that means the bus is typically symmetric, then the S of the bus link from Moon Valley to San Pedro is a probable missing S, right? It's a very simple example of the link prediction task, because this data graph is incomplete. There's some bus direction. This may be correct, but neither given nor intense. So we should predict as the bus direction here exists or not. And for link prediction, to solve the task for type and identity links, they can be addressed using general link prediction techniques. For the particular semantics of type and identity links, they can be addressed with custom techniques. We have the other task called link discovery. Thus, the task related to generate links across the knowledge graph is quite similar between link discovery and link prediction. Because to discover the link, we should base on the link prediction results, right? Link prediction is often addressed with inductive techniques or using knowledge graph embeddings and rule Bayesian. For example, to predict the missing link or the bus link from Moon Valley to San Pedro, we can use knowledge graph embeddings. In this approach, we may detect that given an edge of the form, the bus link from X to Y, a missing link S from the bus link from Y to X has a high plausibility. That's the way we base on knowledge graph embeddings. The other approach is we can use the symbol-based approach to learn the high-level rule. Thus, if we know that we can learn from a rule from the graph that if there exists a path direction from X to Y, then there's also exists the path direction from Y to X. Thus, the rule can be referred to or predict links, new bus link. I can explain it from this figure. If we consider the bus link, we learn from the data graph. Thus, if there's a bus link from Puerto Varas to Puerto Montt, there's a bus link from back from Puerto Montt to Puerto Varas, and it's similar to this the bus link between Puerto Varas and Osama volcano. Thus, we can learn the high-level rule expressed by this. Then we can apply for the link between San Pedro to Moon Valley. In this way, because there exists a bus direction from San Pedro to Moon Valley, then the bus link from Moon Valley to San Pedro is forever to visit. The tiling prediction task. In this task, only one edge label type and typically fewer distinct values classes than other cases. Dedicated techniques can be leveraged controlling the specific semantics of type links. The task can be reduced to a traditional classification, training models to identify each semantic class based on features, for example, outgoing and or incoming edge label on their instances. For example, the task we predict the type of the node Iquique and Easter Island, given that the nodes Aurica, Calama, Puerto Montt, Punta Arenas of the Thai city. Yeah, in this figure, they are given that Aurica, Calama, Puerto Montt, Punta Arenas, and also San Diego of the Thai city. Then we should be the Thai Iquique and Easter Island. Actually the links between these two nodes has the flight link in both directions, similar to these links. So we can predict that Iquique and Easter Island are also the Thai city. It's a good feature for prediction that we consider the presence of edges labeled flight to or flight from the nose. And the graph neural networks can also be used to classify nodes. For the task identity link prediction, well, we will search for the nodes that refer to the same entity, but are not stated to be the same. We determine that which two nodes when present the same entity. In more general data integration setting, the task is analogously entity matching. There are two types of matches, value matches and context matcher. If we consider the value or, to determine the similarity, we consider the values of the two entities on a given property. For example, similarity matches on the strings, numbers, or dates, and etc. For the case of context matches, we will consider similarity of entities based on various nodes and edges in the graph. Let's take an example. We consider two entities, Easter Island and Rapa Nui, and we try to determine that these two entities are the same or not. If we approach with value matches, we can compute similarity from their values. For example, population of 7,400 and the population of 7,500, they are quite similar. And also we can consider the string name of the node, Easter Island and Rapa Nui. Of course, they are very different. So following this approach is very hard to determine that the two entities are the same or not. If we approach with context matches, we can compute similarity based on the surrounding information. For example, similar latitude, longitudes, and population, etc. For the latitudes on the Easter Island, 27.74, compared with the latitudes of Rapa Nui is 27.8. Similarly, the longitude of Easter Island 109.26 and the longitude of Rapa Nui 109.2. Similar. Also, the population is similar. So, following this approach, it's easier for us to conclude that these two nodes are the same. For the task identity link prediction, pairwise matchings would require complexity of O or n square comparison for n number of nodes. So it's quite high complexity. How to solve this issue? Locking group similar entities into blocks based on similarity preserved in keys. For example, if matching places based on the latitude and longitude, and then blocks may represent the geographic region. Alternatively, the windowing in groups or entities in similarity preserving order or multidimensional spaces. Consider searching for similar entities, for example, space-time spaces with Minkowski distances, or autodromic spaces, and etc. The reasons can either be pairs of nodes with a confident to be the same entity, A crisp identity links extracted based on a fixed threshold or binary classification. The node address may be consolidated for confident identity links. For example, Easter Island may be selected as the canonical node and merge the address of Rapa Nui onto it. Then we can find that the world heritage size is in the Pacific Ocean. Based on the consolidated subgraph, World Heritage Site is named the Easter Island. Thus, is in the Pacific Ocean. That's very interesting if we can combine the surrounding information to two entities representing the same place. We can combine the information. Let's cover the first section. Let's move to the second section, correction. In this section, we will discuss the fact validation task and inconsistency repair task. But first, let's see what's the correction. As opposed to completion, we specify new address in a knowledge graph. Correction identifies and removes the existing incorrect address in the knowledge graph. The principal approaches for knowledge graph correction is divided into two main lines. Fact validation. This assign a plausibility score to a given edge, typically in reference to external sources. The other task inconsistency repairs and resolves inconsistency found in the knowledge graph through ontological issues. The task fact validation or fact checking involves assigning plausibility or veracity scores to fact edges typically between 0 and 1. An ideal fact-checking function assumes a hypothetical reference universe, ideal knowledge graph, and will return 1 for the fact being true, while returning 0 for being false. The fact validation often considers online assessment of edges given as the input, whereas link prediction is often an overlay task that generate novel candidate edges to be assessed from the knowledge graph. Works on fact validation are characterized by their consideration of external reference sources, which may be unstructured sources or structured sources. For the unstructured sources, the approach just based on this assume that they are given a verbalization function. For example, rule-based approaches, encoder-decoder architectures are central that can translate edges into natural language. The approaches for computing the plausibility of facts in natural language is called fact finders, which can be directly employed. Two mutually dependent scores limit the trustworthiness of the sources and the plausibility of facts are then calculated based on this graph, where the fact finders differ on how they compute these scores. There's the sums, average log, and investment. Sums adopts classical centrality algorithm by defining the sources as hubs with 0 authority score and facts as authorities with 0 half score. The average log extent is with a normalization factor that prevents a single source from receiving a high trustworthiness score by evidencing many facts that may be false. And investment lets the score of facts grow with a nonlinear function based on investment coming from the connected sources. The score of source received from the fact that's based on the individual facts in this particular source compared to the other connected sources. For the case of structured sources, approach typically assume external knowledge graph as reference sources and are based on finding paths that support the S being validated. We have unsupervised approaches, search for undirected or directed paths up to a given threshold length that support the input edge. The relatedness between input edges and paths is computed using a mutual information function, such as a normalized pointwise mutual information. And supervised approaches, they rather extract features for input edges from external knowledge graphs and train a classification model to label the edges as true or false. An important set of features are method paths and code sequences of predicates that correlate positively with the S label of the input edge. For the inconsistency repair task, ontologies can contain ASIAN such as disjointness that lead to inconsistencies. Such ASIANs can be provided by experts. They can also be derived through symbolic learning, and they can then be used to detect inconsistencies. With respect to correcting an honest graph, however, detecting inconsistency is not enough. The techniques are also required to repair such inconsistencies, which itself is not a trivial task. For example, let's consider if we have an instance of two disjoint classes, such as San Diego is a Thai city and airport, which are stated found to be disjoint. To repair the inconsistency, it would be preferable to remove only the incorrect class. Then which should be removed, city or airport. To business tasks, one edge can be involved in many inconsistency, and one inconsistency can involve many edges. The issue of computing repairs becomes more complex when enhancement is considered, where we not only need to remove the stated type, but also all the ways in which it might be entered. For example, we remove the S San Diego of the Thai airport. It is insufficient if we further have an S Arica with a flight to San Diego, combined with an Asian flight range to airport. Topo and others suggest potential repairs for such violation. by remove a domain range constraints, or remove a disjoint constraint, or remove a type edge, or remove an edge with a domain range constraint. Where one is chosen manually. In contrast, Fonati and others have proposed an automated method to repair inconsistency based on minimal heading sets, where each set is a minimal explanation for an inconsistency. Let's cover the second section. Um, Actually, the last section are the refinement tasks. We should be represented by Ihanson, but we cannot contact with him. And also, this section is very short. So if someone wants to read more about other refinement tasks, you can take a brief look at the section or connect with Ihanson for more information. And this ends the end of our presentation. Thank you for listening.